like to start. We distributed already the 10th exercise sheet. And I would like to give a few comments about this sheet because they can be useful also for your projects. So what we do in this exercise sheet is once again revisit this hanging chain example. We debated about should we always do the same example or not, but the advantage of always doing the same is that you can focus on the concepts that we want to look at, which are the differences here. And this exercise will build on a new computational tool which I think can be very powerful for many purposes. And what we do is actually we install a language extension, so to say, you could think of it, that's called Kazadi, which you can call from MATLAB and which will internally build up the functions that you define. Like when you say, I build up a function, then Kazadi internally builds in its memory this function. And afterwards, this function can be called at the speed of a compiled C function, which is the first advantage. So you don't have to go via very slow MATLAB code when you call this function. But more important, it also delivers derivatives of arbitrary order to any optimization tool that is also coupled to Kazadi. And so you don't need to care about derivatives anymore. And this is something that is very important in practice because otherwise, if you remember at some exercise, we spoke about algorithmic differentiation and then you can do it efficiently. But then if you want to use it with fmin_con, you would have to pass the derivative Jacobian to fmin_con yourself in MATLAB. That means building it first and then passing it at the right moment. And all this can be automated, and in Kazadi this is automated. So you will actually just construct a function that defines your function, your optimization problem, more or less like we do it on the blackboard. Then you ask Kazadi to solve it with a solver, and in this case we want to use the solver IPOpt, which will be based on an algorithm that we draft today. So I explain today how this algorithm works in principle. It's called an interior point method for optimization. That's the name, IPOpt. It's a very good solver. And it's also a very fast solver. So you get this solution at a fraction of a second, and then you have solved this chain example, and the exercise is mostly about looking at the solution and analyzing the results in terms of optimality conditions. I'm really sorry. This will be horrible, more horrible than for you. It will be for the video watchers. I can just tell you. Okay, maybe what I should do is speak a bit softer, and then even if it's a bit strange, maybe you could just move a bit to the front, and I speak as soft as I can. Okay, so we are in chapter 14 on algorithms for inequality constraint optimization. And the task that we are confronted with remains throughout also today's lecture, the task of minimizing a function subject to only inequality constraints. And h was a function from Rn to Rq. So all dimensions are specified. We left out equalities for simplicity because it would just mean a lot of extra notation. What we did last time was looking at the QP solution, just in the case that this f is a quadratic function and h are linear functions. And we spoke about one specific algorithm that's called an active set strategy. So what we have introduced is an active set strategy that actually fixes some of the inequalities and makes them basically equalities, fixes them, and it then solves an equality constraint QP, which we know can be done with just a matrix inverse, and then checks if this solution satisfies the KKT conditions or not. And if not, then it is an active set strategy tries another active set by changing one of them, adding one constraint to this active set or removing one. And the way how they do it is different, and we discussed briefly inwards the primal active set strategy. I will not go in more detail in this, but I just want to recall also the KKT conditions for this problem, because we will need them again and again. That's what we want to solve. So it was this set of non-smooth equations which was saying that we have an optimal point. Maybe I omit the star for a moment because every quantity here has a star anyway. So this is the Lagrange gradient that should be 0. The multipliers should be positive, and the product of multipliers and inequalities should be 0. And here is a very compact way to write what I want to say, namely that the H and the mu should both be positive for every component, and their product should be 0 for every component. This compact way of writing things is not the only one, because they are positive. The fact that their scalar product is 0 is actually equivalent that every component must be positive, must be 0. But equivalently and a bit more related to the algorithms will be this way of writing where I is going from 1 to q. So we require these 3 conditions for every index, and we call these conditions together the complementarity conditions, and that's the whole difficulty of inequality constraint optimization. But please recall this is what we want to solve. And if we would have a fixed active set, if we would know the equalities which are active, then we could just look for a smooth system of equations and check the others, so to say. But unfortunately, this is not always as easy as for QPs. And so what we want to do today is I want to extend into nonlinear inequality constraint optimization. And the first algorithm that we look at is called sequential quadratic programming. And sequential quadratic programming is exactly based on the idea that you can solve a QP already. I mean, if this would be quadratic, we know how to solve it with an active set method as one example. But then if we know how to solve QPs, can we use that knowledge maybe to solve NLPs? So this problem here I call the NLP, and I will refer to it from time to time. So the next section is about sequential quadratic programming. And again, this programming stands not for the art of a computer scientist, but for optimization. Sometimes it's also called sequential quadratic optimization. But now still people talk about SQP. So the task is the same. We want to solve the NLP, but for general differentiable functions. F and H should be differentiable function, but not necessarily linear. For F and H nonlinear, smooth. So if they are smooth, sufficiently often differentiable, then we can differentiate these functions. But just the fact that we can differentiate them doesn't mean that that we end with a smooth root finding problem. And this is due to these non-smooth KKT conditions. You remember this picture that we always put there. If you have HI and MUI, the allowed points are actually these ones. So with this non-smoothness we have to deal somehow. And one way to deal with it is what the sequential quadratic programming does. It actually just says, okay, if I look at this NLP and this is differentiable and smooth, then I can make a Taylor series of it first or second order. Same thing for the age. But it seems that this inequality is something that introduces all these non-smoothness. So why don't we just keep the inequality and let the QP solver deal with it? So the idea here is, as the name already says, solve a sequence of QPs to get a better approximation. It's a bit like Newton's method or Gauss-Newton's method, so you have some quadratic approximation. And so these should be quadratic approximations, and you remember when we did the Newton's method, there was always a first interpretation which was just linear algebra, so you invert the system, but then I already mentioned there is a second interpretation that you could say actually it is as if you would just expand your problem and solve a QP. And now we take this equivalence that we took from Newton's method and where we had two variants, namely variant 1 or one way to look at it and the variant 2 for equality constraint. Here we directly only do the variant 2 and we just say, okay, we borrow this idea and afterwards we prove that this will converge. So which QPs do we solve? So at an iteration, at x, maybe at xk, yeah, so this is current iteration, solve the following QP. So which QP do we solve? We solve a QP which is evaluated at the point xk, so the Taylor series and so on should be at fk. So what we will do is we will do a QP in the step. So like before, it's a step from the current point that then we can take as the step in which we want to go with our primal variables. I call it little p. And what we take here is a Taylor expansion of our objective, but it is actually, okay, there is one term that I could usually drop, but I write it once just for the fun of it. Here we have the gradient of the objective times p. And then there is a second order term, and we will specify it later. P transpose B K P. So this matrix we call again the Hessian. And what will we take as constraints? So until here, nothing new, right? And maybe I should say this again. This term we don't need. We can drop it. It's just constant. It will not determine the P. But now what we do for the inequalities is also we do a Taylor series for our inequalities. And maybe I write it with a nabla symbol now that we use it so often anyway. It's only depending on one quantity, so I don't need, it's nabla h of xk transpose times p. Please keep in mind that this is a whole Jacobian matrix. And now we have these inequalities, and the decision in SQP methods is just to say, okay, we keep it an inequality sign. We don't make anything with it. We just formulate that problem and we let a QP solver do the job for us to solve that problem with an active set strategy and all the complicated things behind. QP solvers turn out to be very fast and reliable and efficient nowadays, so that's not a bad idea. So what we get basically is we input into this an xk, and also, I should say, in reality, we also input a bk, because we need to decide on these two things. Yeah? Then this machinery is solved with the QP solver. And what it spits out is a p. And maybe we call this p pqp. And what it also spits out are multipliers, if we like. It could also tell us the optimal multipliers, and I think I should also give them the right symbol, and I also call them mu QP. And implicitly, of course, the QP solver will tell us that there is an active set, and some of these are active, some of the inequalities are inactive, and so on. So we do that, and what do we do then? We will actually use then xk plus 1 is given by the old xk plus the p qp, which depends on xk and bk. So I put this into brackets to just express the fact that these things depend on, these are actually functions, very implicit functions, xk and bk of our data that define the problem. Possibly with some line search, so maybe this is a bit shorter, and then also the multipliers we could, please keep in mind that for the b, depending on what approximation for the Hessian we want to choose, we might also need multipliers, and if we do need multipliers, then we should also keep track of the current multipliers. So we would also have uk plus 1 is equal to, and here we would actually take the old ones and multiply them possibly with 1 minus t, and plus the new ones, mu qp at xk beta k times t. So that's a linear combination that's consistent with what we do here. Here we have the step, here we have the new absolute value, and there are different choices on how to update them. This is something a bit optional. For example, if we would do a Gauss-Newton Hessian, you remember for Gauss-Newton we will not need anything about multipliers to define our Hessian B. So if we take the Gauss-Newton method, this is not needed. We don't even need to look at the multipliers of our QP. Yeah? So the QP solution, the primal solution, is the most important part here. So that's the algorithmic idea. And the question is if that is a good idea or a bad one. So intuitively it makes sense. So if I just summarize what is the intuition behind this algorithm, you linearize what is smooth, and you do not linearize what you cannot linearize because it's inherently non-smooth, namely the complementarity condition. So, yeah. There are actually several perspectives to look at this algorithm, and there's one perspective that I want to give you before we go on, which is a little addition to the script, which I still need to update to it. I would like to write down what are the KKT conditions for the QP, just to get used also to. So KKT conditions of the QP. So maybe we should first write down what is the Lagrangian of the QP. It depends on P and mu. Yeah, and I omit all the dependence on X and matrix B and so on. But what will it be? It will be, let's drop this constant term here. So we have nabla f of xk transpose P plus 1/2 P transpose B Kp, and then we have the inequalities which come with a mu transpose and then h of xk plus nabla h at xk transpose P, and that's it, right? So these are the inequalities summed up. And with a Lagrangian we can now form the KKT conditions. So the KKT conditions of the QP follow now. So it's actually nabla L QP equals 0. But what is it? It's actually just saying that if we differentiate that with respect to P, it says this thing, f of x plus bkp minus, and here, this doesn't depend on P, but this does. We need to transpose it to get the gradient, and so what we get is actually nabla h of xk times mu. And this should be 0. This is the KKT conditions of the QP, the first one, but then we have others, but the others are quite trivial. Actually, it's h. I put the index here, xk plus nabla h I xk transpose times P. That should be bigger than 0 for all I that are from 1 to q. And also the multipliers should be bigger than 0. Mu I should be bigger than 0. And the product of mu I and this expression here, hi of xk plus nabla hi xk transpose p should be equal to 0. So we see there are some complementarity conditions because we have a QP, but these are the conditions which we solve actually in each iteration with this QP solver. And afterwards we have found a point that satisfies these equations. And now we can compare these KKT conditions with the KKT conditions of our original nonlinear programming problem. And we can look at them and see if this is indeed something like a linearization of those. So if you would linearize that thing with respect to the first line of the KKT conditions with respect to x, then you would get a Taylor series where this term is the constant part, and this one is actually the dependency of this whole Lagrange of this whole function with respect to x times p. P is actually delta x, so that's a step in x's. So we see immediately that if that should be linearization of the first column, then this b should be a second derivative of the whole thing, or actually a first derivative of what we see there, which is a second derivative of the Lagrangian. So if that would be bk would be similar to the second derivative of the Lagrangian of the original problem at the point xk and mu k, then this would be a linearization of the first line. And with respect to mu, this system here, the first line is already linear, so this is not changing anything. Everything gets a bit complicated due to the fact that we have p is the step in delta x, and mu is actually the old mu plus the step in delta mu. But if you interpreted it from a Newton's perspective, this would be exactly a linearization of the first line if that would be the case. Now this is also a linearization of the second line, right? It's just a Taylor series of the function h. So that sounds good. So we have here this thing bigger than 0. The mu is it's a linear equation. So if you linearize that, it stays the same. So that's what this thing is, also a linearization. So everything until now would be just a linearization, Newton's method like before. But what we do here is a bit different. It takes the mu and it takes a linearization of the h. But it keeps the product here. And the product, of course, if you would linearize that whole equation with respect to x and mu at the same time, there would be no cross term with this mu and that p. But here this is a nonlinear equation. As you see, mu times p. So in the unknowns of the subproblem, in the unknowns of mu and p, this is a nonlinear equation. So this is slightly different than linearization, but on the other hand, it's linearization in the spirit of keeping whatever you know you can differentiate it, but keep, so to say, the convex structures, and inequalities are convex structures, so keep that intact and don't mess with it. So we actually write down this QP, and this is just a way to look and interpret it. But I just want to point out that here we have a quadratic term in mu, I, and p. So it's a nonlinear equation, so this is definitely not a linearization. On the other hand, you could say it's a very careful linearization which takes care to keep track of the underlying structure. Okay, this is just about the interpretation so that you get the connection a bit to this Newton's method. If we had only inequalities, everything would be, of course, easier. I mean, we left them away here, but then there would be just a linearization of the equalities and everything 0, and we are done. But due to the complementarity conditions, in particular this product, we get this necessity to invoke a QP solver and do something more per iteration than just solving a linear system. So this was just a remark. This whole blackboard, the left side, is a remark that's not needed actually for the flow of the argument that comes. The real argument that I want to discuss now is if you would start close to a solution. So if we start close to a solution of which we know that it is a solution, does this algorithm actually converge to the solution? in the sense that it would identify the right active set and then basically perform a Newton's method. And that's what I will claim and then also frame in a theorem. We show that the active set is correctly identified when xk is close to x star, and x star is a solution that we want to look at, is correctly identified by the QP solver, of course. And if the QP solver has correctly identified the active set, then you remember what a QP solver does. It's actually treating the active constraints as if there would be equalities and disregarding the others and just checking that they are satisfied. And so then it basically boils down to a Newton's method for equality constraint optimization with the same convergence properties as before. And then SQP becomes a normal Newton type optimization method. Maybe I should give a name to the active set, so let me just call it A. Yeah, so this active set at the solution, you remember A is an index set that selects some of the indices from 1 to Q. And if this set would be correctly identified by each QP solver solution again and again, then what we know is that basically the QP solver solves just the root finding problem that states here these two conditions. To solve this problem, actually, and so here we can already add the index A, so we would only be interested in the active indices, and also for the equalities we would have only this would be a root finding problem. If we know the active set, we could just solve this root finding problem. It's actually quadratic. It has just n variables x, and it has the corresponding number of multipliers corresponding to the number of equalities. So it's again, it's just an equality constraint problem. We could solve that problem with any Newton type method we like, and afterwards check that the active set that the other constraints, inequalities are actually positive and that the multipliers have the right sign. And if these two things are met, then we would be fine. And what we will now show is that the SQP method, if this QP at the top is formulated close enough to a solution, will exactly basically solve the linearized version of that. So in particular, most important, it will keep the active set at the right, at the active set of the solution of the NLP. So let me just prove and cite a theorem that is due to an American optimization scientist called Stephen Robinson, still alive, I hope, because it's a long time that I didn't meet him, but when I met him, he was already, I think, 80 years old. So it's due to Robinson. It's a very fundamental, but also not too complicated result. He proved it in more generality, I should say, but what we will do is do what we can really and what we really need. So fx star is a local minimizer of the NLP. So of this NLP that we have stated on top. And we assume some things with LICQ. That's the typical thing we have to assume. We will also assume second order sufficient conditions. So positive definiteness of the constraint Jacobian. I don't know if we even need that, but I will assume it anyway. And then we will also assume something which is strict complementarity. I think I defined it, but I recall it. It means that the multipliers and the inequality constraints are not at the same time zero. So that means all multipliers of active constraints are strictly positive. Yeah, that's what strict complementarity means. And xk close to x star. And we need to define also, we need to make some assumptions on something else. Now we have made an assumption on the x, but also the b. We should also assume that the QP is convex. That means that the bk should be positive definite. Otherwise, we wouldn't know if the QP solver actually finds a global solution. So we will make our bk positive, and we will assume also, but that is something which is locally implied by second order sufficient conditions, so we could actually state it separately. And bk is positive definite on the null space of the linearized constraints. On the null space of the linearization of the active constraints. In the QP. So basically, that means SOSC in the QP. That's what we really need. Maybe I drop it here. It's related, but we don't need that for the proof, so I can drop it. So we need second order sufficient conditions only in the QP. And what this theorem says, and now I need the other blackboard, the main point, then the QP, this above QP, this one, maybe we should give it an index. Just call it with an index. So the QP has the same active set as the NLP at x star. So that's exactly what we would like, namely that the QP solver, so now I moved the blackboards, right? That the QP solver that solves this problem basically identifies locally the right active set, which we don't know that it's the right one because we don't know the solution, but the proof is if we know a solution and we solve QP nearly at the solution, does the QP solver give us the right active set, and if yes, then we are happy. And if we are far off, then there's another discussion about globalization and global convergence and so on, but locally at least this theorem ensures that we get to the point where we basically solve a smooth root finding problem, and then the only question that determines our speed is how good our Hessian approximation is. So about the meaning of this theorem, is there a question or some remark or something you would like to ask or comment? If not, then I would go on by proving it. Yeah. And maybe during the proof, some of the concepts will even get clearer or not. So the proof of this theorem goes as follows. We will actually look at the solution of the QP at a point which is independence of x and b. So we basically have a kind of implicit function that is implicitly defined via the QP. And let me just first define properly the active set. So A is just the active set in our previous notation of the true NLP at the point x star. So that's the correct active set. And then we also define, as before, H, A, and H, I, mu, A, mu, I, as before in the QP solution. You remember these complementary sets of active and inactive constraints, which we can get by reordering the components of the vector. So we just put them all into one vector to have a nicer notation. Yeah. What we will now do is we regard a root finding problem, which is actually not exactly this one, but it's very related. It's a root finding problem which defines a solution to the QP if the active set would be the right one. So we actually go implicitly. So we regard the root finding problem as a function of x. So nabla f of x plus bp minus, okay, this constraint here at x times mu a, and I give an index QP here. I think maybe it would be nice, and I will change the script accordingly to put a QP here as well. So I basically take the first equation from our KKT conditions, it's this one, but I will only define it for the constraints and for the multipliers which are active. And I will also state a second equation which says that h of x for all these active constraints plus the Taylor series of this h, which also depends on x, times pq, that this thing is also 0. So this is an implicit equation system in unknowns. What are the unknowns here? It's p, qp, and mu, a, qp. So these would be the unknowns of that system, and the parameters on which the system depend are x and b. Okay, so this is it's a linear system of equations. If you see it for b and mu, it's a linear system of equations. You could even actually write it down quickly if you like. I didn't do that before because I didn't look at it from this perspective, but now if I look at it, I see that p and mu are actually obtainable as an explicit expression as functions of x and b, so why don't we do it? So as variables, they depend on x and b. So x and b are the data of the QP that will change. And of course, if some pqp and some mu qp satisfy these equations, then they are potentially a solution to the whole set of KKT conditions if the other parts are also satisfied, like yesterday like last time when we looked at the QP solution. So let us first define these things. So then explicitly, this is something I just discovered now, so let's use it. Explicitly, we have, so what do we have? We have p, qp, and mu qp given by, so this is a linear system. What are the residuals? This is a residual and that's a residual. What is the matrix? It's a b and this thing and that thing. So what we get is actually a minus sign here, a b, a nabla h a at x transpose, a minus nabla h a x. So this is the transpose Jacobian. That's the matrix here. This matrix is inverted and multiplied with a residual, which is nabla f of x, and here it is h a of x. So that's just an explicit solution of this whole thing. And we will write from now on actually QP as a function of x and b, and mu QP A as a function of x and b. Okay, and what we want to show is that this explicitly constructible thing, which is a smoothly depending on x and b, that this thing is actually is the solution of the QP, the unique solution of the QP, if the x is not too far away and if the other conditions are met. So note that this invertibility of this matrix is ensured by this last condition. Because this matrix is invertible if, okay, LICQ holds, that means that these things should be independent and this B should be positive definite on the null space. So existence from LICQ and second order sufficient conditions for the QP. So what we still need to prove is actually that this thing is a solution to the QP, and also, that's actually what we want to solve. What I also want to solve to show is that it satisfies QP at any point at the point x star for any b should be equal to 0. So we don't do a step. At that point we have the solution, and the multipliers mu QP A at the solution also for any matrix B should be equal to the multipliers at the solution, which I didn't introduce here in the theorem definition, but they basically correspond to the solution. So these are the multipliers, of course only for the active constraints. So maybe I should first summarize what we want to do. This is already part of what we want. The other part I didn't formalize yet. So, and what we want is that actually that the inequalities which are not active at a corresponding point are remaining not active, even if we change a little bit. So that they remain positive. And what we also want to show is that the multipliers of our active constraints, so these multipliers QP, which depends on x and p, that they also remain positive. So these are the things that we need to show in order to be sure that this solution, this explicit solution of our QP, or of the QP with a fixed active set, that this is indeed the solution of the QP. Yeah, so it should satisfy all these conditions. And so let's prove these things step for step. So maybe I give them numbers, 1, 2, and 3, and we go through these conditions one after the other in order to show that they are all the case. So maybe let's just look at if x star would be, if we evaluate this thing at x star. Now then actually we want to show that only 0 and the right multiplier solves this question, this system. It's equivalent to this system. So I could also just look at this and see if I put x star here, 0 here, 0 here, and the right multipliers here, indeed it solves it, because then I get the KKT condition at the original point. So it's nabla f at x star minus the transpose Jacobian at x star times the right multipliers should be 0, and that is the top of our KKT conditions. The second one is also clear. This thing is 0 at the point because it's the active set at that point, right? So h of x star is 0, and plus 0 is also remaining 0. So 1 due to KKT of the NLP at x star. And I should say uniqueness and existence follows already from the invertibility of this metric. So that these things exist is not a problem. So 1 is already settled. So now let's look at 2. So what we want is now to show that all these inequalities that are not active are remaining not active if x star is, if xk is not too far away from x star. You have a question?
Yeah.
Okay. I just looked at. So first of all, it was a double thinking, right? The first thing is I just said this solution is unique. So the solution to the system is unique. So when it's unique, then if I find one solution, then it is this solution. And then I just say, okay, I know that the KKT conditions hold. Actually, maybe it would have been nicer if I would have had put here the star, because it's the same star that I use here. Right, so this star, here's everywhere a star. Okay? And so the first condition, if I put in p equals 0 and the right multipliers, the right multipliers, maybe I should also say one thing because of this division here. I have, of course, that mu star is equal to mu a star and mu I star, where this first thing is actually something which is non-trivial, but the second thing is 0. Yeah, so the second multipliers are anyway 0 because they are not active. And because they are not active, they don't contribute to this sum anyway. So actually setting all the other multipliers to 0 and this verifies this equation. So if we put in x star and the right multipliers for the active constraints and then multiply them with the right components of the Jacobian here, then we get something that must be 0 because it's only modified by more zeros in this expression. So then it's the same as that expression. And for the h, we see that the inequalities here are active, so they are exactly 0. But there are some others that might be inactive, and so what I should also stress is that the inactive constraints at the solution, because of strict complementarity, are positive. So all the other constraints are anyway positive, so they also satisfy this. And then the complementarity is, the multipliers are only positive because they were the positivity is not checked here, but we know that it's positive because it is the mu star is the solution of the NLP. Does that partially answer your question, or do you want to dig deeper? Yeah, we can also dig later. Other questions or interest in the same question? No. Okay. So we go on with our route. So these were remarks. Huh? So this is just something else. Maybe first on the storyline. So if we have shown all these things, then we have indeed shown that these expressions solve our QP. Yeah, because then this is the inequalities of our QP, that the others are actually also satisfied, and this means that our multipliers remain positive, so they never got in negative, which would be the only problem. Yeah. So I should maybe, before I prove anything, then P, QP, and mu A, QP plus zeros is a QP solution. Yeah, so if these things hold, then we really have a QP solution, these two things. Because this holds already, so if these two things also hold, then we have complementarity, we have still, and we have all the equalities are satisfied, the inequalities and the multipliers are positive. So let's go on. How can we prove this, the second property? So when we change x a little bit from, so maybe I evaluate that function first at x star. If I evaluate that whole function at x star, then PQP at x star and B, what is it? This is 0 anyway. This is not 0, but it's strictly bigger than 0, so this doesn't matter. So this is strictly bigger than 0 for any component. And by continuity, if this whole expression, I mean this P is continuous because it's, here we have even an explicit way to write it down. And here we have the H, which is also a differentiable function. The Jacobian here is a differentiable function. So everything is by continuity. Actually, the Jacobian is a continuous function because it's C1. So by continuity, 2 holds. When does it hold? For xk, or for x minus x star small. So if we have it small enough, then this whole expression will still be positive. Just modify it a little bit. And now the 3 is the same. Here we have something also, mu a QP at x star. What was it? It was actually, just we discussed about it before, it was this thing, it was the inequality multipliers at the solution, which are also strictly positive. That's where the strict complementarity helps us here. And then we have the same. By continuity, 3 holds. 4. So, sorry, here I missed the B. X star minus x minus x star small. Maybe you wonder a bit, why don't we have the dependence on B, right? So I didn't really mention the dependence on B here. But here we see that if anything depends on B, then it's via this term, and this is 0 at the beginning. I think this argument doesn't hold. I think I would need to think a bit longer to rule out that this can, so to say, jump because we make a different B. I didn't look at continuity with respect to B, but if you think of it, the B here, I mean, we made some assumption here, namely that this whole thing is invertible, and probably to make it really, really correct, we need to have, and that's what we would like to, we would probably have to bound somehow the inverse of this matrix to make it suitable. Because just saying that this is positive definite, it could become very degenerate, and maybe there could be some discontinuity due to the B here. So I think I need to think a bit more about it. But roughly speaking, you got it, right? So these things are continuous, at least depending on x. If I would add here and B sufficiently close to the original B, then everything would be fine anyway. Actually, I could say that the B should be equal or similar to the B on the null space of the active constraints, and I could be lazy, but I think it's not very strongly depending on B, and I need to think about that a bit more. I just realize it now. But actually we are even ready now, because what we wanted is to show that if you solve this root finding problem, you get something which is exactly equal to the solution that we want at the point which is the solution, and approximately equal to that solution, but at least with the right active set, then that the solution to this system still satisfies the same the KKT conditions of the QP with the same active set for small perturbations. And that's what we need. And that means that if we are close to the solution of the NLP, we formulate a QP there, then magically the QP solver will identify the right active set, even if it was not in your, if you didn't know about it. So the interesting thing is that again and again in every iteration of this SQP method, you formulate an inequality constraint QP and you leave it to the QP solver to identify which are the active and which are not the active constraints. And again the QP solver will identify the right active set if you're close at the solution. If you're not close to the solution, somewhere far away, it will find some possibly different active set and then make improvement and trial iterations until eventually, if it converges, it will identify the right active set and then it will do, for example, quadratic convergence to the solution because it always has the right active set. So that's a theorem that I wanted to share with you, which is at the basis, I would say, of local convergence of SQP methods. The method is quite easy to implement if you think of it. Once you have a QP solver and you would be deciding that you just do full steps, then you could just do this, you solve a QP, you do a step, you solve a QP, you solve a step. And then there are only a few questions, and these questions I think I will discuss in the next. No. I feel like I still do it now. It's okay? If you still have energy, it's fitting actually this blackboard. So what would you do in order to make this a full-scaled, nice algorithm? And I will state one algorithm that is due to Mike Powell, also a senior optimizer. And this algorithm, which I call the classical SQP algorithm, was invented sometimes around the early 1980s, and that sparked a revolution, I would say, in nonlinear optimization, because for the first time people could practically solve interesting nonlinear optimization problems, and they did so a lot, and that was an important algorithm, and is still used nowadays. For example, fmin-con as a base algorithm has this algorithm. So what we do? So first of all, for an equality and inequality constrained NLP. Yeah, so let's introduce the equalities again. So then it's straightforward to solve, to add here some linearized equalities, right? So that's not a big issue. So what do? We first solve an inequality constrained, inequality and equality constrained QP in each iteration. So that's the basic vehicle here, what we just described here. But then there's another question, so how do we do line search? And if we do line search, we need to decide when do we accept a step and when we don't, and how far do we do a step. And there we need a merit function. So we do line search. And we use a merit function. And this merit function is like the T1 that we introduced before. This was the one that we used for equalities, which consists of the objective. And then we add some contributions which are due to the violations of the equalities as before, and each of them is weighted with a factor that we call sigma I. And then we also add some violations of the inequalities, hi, and they are multiplied with some other factors that I could call tau I. Yeah? And these are factors that need to be high enough. And what I wrote here is actually, I will only be interested in violations of inequalities, and the violations are the ones where actually the max of 0 and minus h is positive. Yeah? So actually minus h is max of 0 and h. Yes. Oh, no, I think I should just take, this would be nicer, min of 0 and h. So if h is positive, then the min of these two is 0. There's no penalty. If h is negative, then the min is achieved for h, and we take the modulus, and then it's a positive penalty. So this is a non-smooth function. At the inequalities, of course, it looks like this. So if the inequality is violated, then it starts to penalize it. For the equalities, it's even like that. So it penalizes all deviations from inequalities. But that's not a major difficulty. And actually, one can show that this thing is also, this SQP method leads to descent in that merit function in each step. And then the third thing is use BFGS or DFP, which is another update which even carries Paul's name, but it doesn't matter. So nowadays people use BFGS. But what do we need to do? We need to think about the difference of Lagrange gradients. And so we need to use the full Lagrange gradient with all the things that we have now, including the inequalities. But that's an easy thing, right? So the full Lagrange gradient is actually this quantity plus also the contribution from the equalities evaluated at the right points when we do BFGS updates. So these are, of course, it's just a sketch of the algorithm. This algorithm can be implemented without too much effort. So I would say if someone wants to do this as a project, to develop your own fully fledged SQP algorithm that is, so to say, including all these things and maybe a few other things that might become necessary when you solve a real problem, that could be a doable project, I would say. But most of you have already projects, so don't worry. So now we have covered in 1 hour only a very large class of optimization methods which are called SQP methods. And at least the basic idea, I think, was conveyed. It's difficult to do an example for this because, it's always involving solving a QP in each iteration, so it's a very high-level thing that you need to do here. But maybe I would like to do one sketch which might help you to, so to say, get the visualization of that. And this is not computational at all, but so you could think of an NLP here, which might have this as an objective, for example, right? And it could have some constraints, like this would be the forbidden zone, and maybe here's another curved constraint. Yeah? So it's one objective and two constraints. Yeah? And I would like to ask you a few questions about the SQP QP. Yeah? Let's assume that this objective is actually just quadratic and that we use a Gauss-Newton Hessian. And then the QP at different iterations will correspond to an approximation of the NLP, which is just a QP. And if we, for example, I don't know where, let's say we evaluate everything at this point. So this could be xk. Yeah? And the Hessian I say I disregard it, so the objective will always be the same because it's a quadratic objective and I do Gauss-Newton, so the objective will be the same. But what will be the constraints now? And so at this point xk, my constraints could be, this depends a bit on the nonlinearity and so on, so let's say this is the point xk. What I know is that they will be linear. So these could be my constraints. So you see they are not exactly the same, they cannot be the same because it's a nonlinear function, but the linearization of these constraints creates a linear approximation of this whole thing. And if you solve this QP now, you will get to a point which is, if this is still the objective, this would be the optimal point. That's the optimal objective of that QP. That would be the intuitive thing. It will identify, it will minimize this objective. Here's the minimum in this feasible set described by the yellow thing. So here we will have xk plus 1. And now at xk plus 1 you will linearize your functions again. And if you linearize these functions, then probably because now we are closer to that constraint, this will be a bit closer to reality, maybe like this. And also, let's assume we got a bit closer to that, so maybe this one will be like here. And then we solve it again, and what will happen is that we find, and now I'll change the color and I'll take this one, that we go here to this solution here, and that will be xk plus 2. And then we linearize the two constraints again. This one will get exceedingly tangential to the right one, but this one might not, because we are still far away from it, so we don't know exactly. And you see the algorithm will converge to some point here, which is actually the solution. And you see already here in this first iteration we have identified the right active set. I should also say, and just as a question to you for fun, it's a task, it's a little question. So if I would be, you remember this was my original constraint, this white one. So what would be the corresponding linearized feasible set from the QP at that point? How would these two constraints look like? So I maybe say this would be x, x, it's not xk. So it's maybe xk minus 1. So maybe it was the iteration before, I don't know. Yeah, just for how would it look like? At this point we know it actually. This is actually the linearized feasible cone, because it's exactly at this point of that. Actually it's the linearized feasible cone locally also here, but only when we are at the boundary of the feasible set, then it is the linearized cone. But usually we are not at the boundary of the true feasible set. But if we would start here, then our feasible set would be something like this. I draw it not too big to not disturb the rest of the picture. But it would be just tangential to the true thing. So you see that the SQP method is in a very natural way. It approximates the feasible set at the neighborhood at which we are, based on the Taylor series of our nonlinear functions. And the Taylor series is tangential to the true boundary when we are actually on the boundary of the true set, but it's not exactly tangential, but it's related to it when we are in the neighborhood of it. Okay, so let's stop for here and have a short break. Maybe let's do a break of 7 minutes and continue 35 past, so that we can still cover one other interesting topic for today. Good. So then I would like to introduce another class of optimization algorithms, which are also designed to solve inequality constraint optimization problems like here, but they address this inequality problem in a very different way. And so this chapter is about what is called interior point methods. It's not a chapter, it's actually a section. 14. Interior point methods. And they follow a very different idea than active set methods or SQP. And actually are able to replace both in one if necessary. So they are an interesting class. And I left on purpose the NLP. We want still to solve this problem. We still know that these are the KKT conditions that a solution would satisfy. But we also know that these KKT conditions are non-smooth due to this complementarity constraint. So now the idea of interior point methods is very simple actually. It is just if something is non-smooth, like this thing, we could try to approximate it by a smooth set. Instead of this thing, we could do something that is close to this, but smooth. And I exaggerate a bit. This could be an approximation of that. And maybe if we make a parameter that makes it from very bad as an approximation, but very nice and smooth, into something that gets closer to the non-smooth set, and then we let this parameter go to, let's say, 0, and at 0 we recover the original one, then we could maybe have hope that solving these smooth root finding problems gives you an approximate solution for the non-smooth one when you drive this parameter tau to 0. So this would be in this direction. So if I start this thing, then I have a tau that is going to 0. So that's already the idea in a sketch. But how does this translate to this root finding problem? So the idea is actually to replace the complementarity condition, the complementarity conditions, by something smooth, by a smooth root finding problem. So that's the first idea, actually, and then the second idea is to make this as similar as possible to the other one by some converging algorithm. So the second part is, and let the smooth problem converge to original one. So one possibility, if you look at these plots, would be actually to just say that the product of mu times h should be not 0, like here, but it can be a positive number that we call tau. And if it's a positive number, then you get these hyperbolic sets. And if the number tau is very small, then it's very close to the set. So what we will actually do is we say, so we call these things the KKT of the interior point method. Yeah? So these are the conditions that say nabla f of x minus nabla h of x times mu. That should still be 0. But then this complementarity condition, I write it first actually, then the mu I times the h I of x minus tau should be equal to 0 for I going from 1 to q. And that's it. And there is, of course, two other conditions, namely that the h should be positive and that the mu should be positive. And if you think of this equation, this mu times h being equal to tau, which I state here, then there is actually one solution where both these things are positive. Yeah? So I should first say for tau bigger than 0. Yeah? So we only choose a bigger than 0 tau. So if we have this root finding problem, there would be some other solutions here. If both are negative, the product would also be positive. And these we call shadow solutions. And we don't like them, of course. They will usually not appear, but if they would appear, we should exclude them, and we would, of course, somehow still require hx bigger than 0 and mu I bigger than 0 to avoid shadow solutions. But I should say that these conditions here are not so important, because when you're close to a solution here, a Newton type method would not likely jump to a very different branch anyway. Yeah? So if you do a kind of Newton type method, then you will always stay close to a solution, and if you are nicely initialized, then you will stay there. Okay, so this is already the full idea. It's so simple. Yeah, you just replace a non-smooth equation system by a smooth one. Just make smooth what is non-smooth, and solve this, and you get a solution which depends on tau. Get solution. And now let's make the right notation. I call it x bar of tau and mu bar of tau. So this is an approximate solution which depends on tau, which solves this root finding problem. So maybe let's first recall. Does it actually contain exactly the right number of residuals and unknowns? So here the unknowns are x and mu like before. X has dimension n, mu has dimension q. These are n equations, and these are 1 to q equations. So we get exactly a square system of nonlinear equations. So in principle, it's a well-defined, nice thing. Yeah, it's actually, again, the implicit function theorem, right? It's implicitly defined via the KKT IP conditions. So that's already one statement of this method. And what we can then actually show, and that we will not show, is that for tau equal to 0, x of tau and mu bar of tau will converge to x star and mu star for tau going to 0. So we will always have positive values of tau, but then we go to 0, and when we go to 0, then actually intuitively this thing will get more and more close to our original one, and nearly non-smooth at the end, and then it also gives you the right solution. But the catch is that we can solve these things with smooth Newton's method now. And of course, if one could say, okay, this is a bit stupid, so we have to solve, actually, we set up something, tau, and then we just prove that if tau is small enough, it gets to this solution. But then why don't we just make it 0 directly, and then we have the original one? So how does this help? It helps in the following sense, that we will actually first make the tau a big one, because then this non-linearity of this thing will be mild. You see, when we make tau smaller and smaller, this gets more and more kinky. That means that the nonlinearity increases significantly, right? So we start with something which is not so bad, solve it, and then we solve it for a smaller tau, but not significantly, actually smaller, but not with a big jump, but actually maybe reduced by a factor of 10. So tau might be divided every time by 10, and then we initialize the Newton procedure at the old solution, and at the end we might converge to some point, for example, here. So the idea is actually to start with a big tau and then solve this with a Newton type procedure, and then when that's solved, then we reduce the tau and solve it again, reduce the tau, and so on. But we will always initialize at the old solution. That's called a homotopy. So that's actually idea 2. So it's actually already mentioned here, and let the smooth problem converge to the original one. Use path following, or also sometimes it's called homotopy, to initialize Newton while reducing tau, for tau going to 0. So how will the algorithm look like? Let me just state it as a very rough sketch. The IP, the interior point algorithm, what will it do? It will rely on a lot of things that we have already done before. It will first start with a big tau. Yeah. So it's significantly bigger than 0. And we choose also some parameter beta, which is between 0 and 1, and which will be the reduction factor with which we will reduce the tau. And so then we will do a loop. And this loop is solve VIP KKT, okay, I think I switched it. Sorry for the notation, so KKT IP or IP KKT doesn't matter, solve interior point KKT conditions to get by Newton's method, right? And get these two values, get x bar tau and mu bar of tau. And maybe I should just introduce an index, then it would be much more logical, and I think I will do that. I will call this tau 0, and then here I will do a loop for k equals 0 to something big, yeah? 0, 1, and big enough. I will get these things. So here I set actually k equal to 0. And here I solve it for tk and tk. So I get the solution, but I need to initialize that at some point. Initialized at, and I call this maybe x x k tilde and mu k tilde. So we need to have some initializations. And so in the start, I also need to define some x tilde 0 and a mu tilde 0. So I need to somehow have already some guess for the solution. Otherwise, I cannot do any Newton's method. Then I initialize at these points. I apply Newton's method. At the end, I will get the solution for the parameter tau. And then I take the solution as guess for the next problem. So what we will do is actually, we will set the starting point, the guess that we need to do, to the solution that we just obtained. For a given parameter tau. And reduce tau. So we say tau k plus 1 is equal to beta times tau k. And then we end. Now, of course, we would stop when the tau is small enough. And you see that actually the tau will be the initial tau times beta to the power of something. So we can actually stop it if it's small enough. I will not specify now how small at this moment, but I want to make a few remarks about this. So I think the algorithm is pretty clear from the picture and also from what I discussed in words, but I just want to make sure that all the points are clear. So we have a Newton's method to find these solutions here. And if we have found the first one, then we can use this solution as initialization for the root finding problem of the next one, and so on. And if we change these things not too much, then we would expect that we remain in the area of quadratic convergence of a Newton's method, so everything would be fine. And now the nice thing is that if we converge to a solution which is here, or for some other variables we might converge to a solution that is here, we never actually encounter this non-smooth point. So we never ever go to it. Only if we have weakly active constraints, we might actually directly converge to this point. And it turns out that interior point methods have no big problem even with that part. But for strictly complementarity, you immediately see that there's never any problem because we will never visit the non-smooth point. But there's a few remarks. I want to make one remark about a name, and that is that these solutions here, x bar and mu bar, for given taus, they are called the central path. So x tau and mu bar tau for tau element in actually 0 to infinity. So this whole curve is called the central path. So So just when you see people talking about the central path, then you know is this curve. And if you want to visualize this central path for a problem like the one that we had before, for example this one, here are the inequalities. Here's this objective, sorry. Then the central path will be, so to say, and I will argue about that actually next hour, but it will be some set that goes through the interior and only at the end approaches the solution at the boundary. And so this would be x bar of tau. In the primal variables and also in the dual variables it will be similar, but this is how the central path would look like, and so it turns out that it's in the interior. Yeah? X bar of tau is in the interior of omega for tau bigger than 0. And this is relatively easy to see. Why should it be the case? Because in our root finding problem, we actually, for tau bigger than 0, the product of mu and h must be positive, right? That means that both the mu and the h must be positive, and that means implicitly that the h must be positive. And positive means it's in the interior, it's not active, so to say. It's not at the boundary of the active of the constraint. So that's why this central path will be something which is actually, it turns out that it will be pushed away from the constraints, the bigger the tau, but then it will move for, here, so to say, tau going to 0, it will converge to this point. We will discuss it a bit more, but I think I don't want to have everything covered in only a few minutes because these methods are too interesting and too important. The thing that I would like you to remember until next Tuesday, is actually this set of conditions. And we will give a surprisingly simple other interpretation to this set of conditions in the next hour. Let's stop here, and actually next Friday I would like to invite you to do the projects, like already at the exercise group. And maybe I should ask Dimitris if this project session will take place here or in another room.
No, it's in the campus.
Okay.
The rules for Fridays, it's written there. It's a bit next to the one where
Okay, so please, if you want to do the projects, and we recommend that, Dimitris will be around next Friday. I will unfortunately not be around this Friday because I have to be in another town, but I try to be also around at some other Fridays. But please come to the campus to discuss with Dimitris about your project, start implementing them, and also you would get feedback maybe during today's exercise session or on Friday if you want to already install Kasari and do some parts of this optional exercise sheet 10. Thank you very much.